Hi, everyone. My name is Roy. Today, I'm going to teach you about logistic regression. So first, before I start, I want to have a quick introduction for myself. So my education background is in industrial engineering operation research. And I have 15 years of working experience in the data science and machine learning area. 3 years in supply chain and logistics, 6 years of fintech experience building credit risk model, compliance, and fraud models. And I also have 6 years of machine learning experience building recommendation engine, seller and product abuse at Amazon as well. So in today's agenda, I'll talk about what is logistic regression, why I use it, the sigmoid function in the logistic regression models, the cost function, how do we derive the cost function or minimize the cost function using gradient descent, and model evaluation. After that, we'll also walk through some example coding for logistic regression as well. So without further ado, let's talk about logistic regression model in a nutshell. So it is a very simple method that's very commonly used in the industry. It is a very fast algorithm for both training and also online inferencing. Because it can be learned incrementally, we can also use stochastic gradient descent to train the model and reach the global minimum rather quickly. For logistic regression, it is outputting a probability. Basically, it's the potential probability, which is easier to interpret compared to some of the other black box model as well. Lastly, this is a discriminative model, which means that there's a lot of model assumption that is being used here. Now, before we start, just want to give you guys some high-level examples of where logistic regression model can be used. So this is a typical way to use it in the industry is doing a binary classification. So for example, when we try to understand whether an email is spam or not, or whether we try to evaluate the online transaction and tell whether they're fraudulent or not fraudulent. And in healthcare, we can say, okay, whether we can classify the tumors being benign or malignant. And for logistic regression, for binary classification, it usually contains two classes. One is a zero class, which is negative class. Usually means it's something that is good. For example, if it's a benign tumor, if the transaction is not fraudulent, or the email is not spam. The other class is one, signaled by one, which is the positive class. So for example, a malignant tumor is considered a true positive class here. Again, so let's recap how we can utilize a learning model before we go into the logistic regression. So here, probably in the previous meeting or classes, you learn about the linear regression model. So what that is that you can take inputs of feature X and feed it into this learning algorithm, and this learning algorithm would output a predictions. And you can use that prediction to classify, the label for this. As you remember, the linear regression model has the function of h theta x equals to theta 0 plus theta 1 times x. The parameters are theta 0, which is the intercept term, and theta 1, which is the coefficient for our feature x. So, before we jump into logistic, we can use this tumor example to illustrate how we can build a model using linear regression to classify whether a tumor is malignant or benign. So here, our feature is just using, simple illustration, just using one feature, X, which is tumor size. As you can see from the chart here, the red crosses at the one yes here are the ones that is malignant. And then the red crosses at the x-axis, which is a no, they're not malignant. And you can see based on the tumor size, obviously, small tumor usually indicate that this is not a malignant tumor, whereas the larger tumor sizes indicate that it is a malignant. If we train a linear regression model, you can see that the blue line here is the resulting training models. And if we put a threshold at 0.05, if we say that if the predictions greater than 0.05, then it outputs, then it is a true positive, which is y equals to 1. If it's less than 0.5, then we say it is a 0, which is not a tumor. By using this threshold, the model could, perfectly identify whether a tumor is malignant or not, right? So you may be wondering, then in this case, we can just use a linear regression model to solve this problem and call it a day. We don't really need to use logistic regression. However, the problem here is that there are a lot of nuances or problems, issues by using linear regression in this classification problem. One is that you can see that for this linear regression model, you can have values that's negative, which is lower than 0. And you also could have values that's greater than 1 as well. And sometimes it's significantly larger than 1, depends on your tumor size. So obviously you could potentially solve it by cutting or capping or capping the value between 0 and 1. But as you remember, the cost function for linear regression is the square of the error term, which is the y minus the y hat. So for some of the larger tumor size indicated here in the red cross at the very right, you will have a large residual, which means that you're going to have a large error term for some of the prediction here. And as we train these models, so obviously this is a very simple illustration. As we go into higher dimensionality of different data, your model could become wildly unstable because some of the predictions are much larger, and which can skew your slope of your models or the parameters of your models, which makes your prediction unreliable for some of these binary classification problems. So now the logistic regression will come to rescue. So the logistic regression model is very simple in concept. And what it does is that it adds a function called sigmoid function to the traditional linear regression model here. As you can see, now we updated the logistic regression model of h theta x equals to the function of sigmoid with the theta transpose times x, where theta transpose x is a linear regression formula. What the sigmoid function does is that it is a term for 1 over 1 plus exponential of negative z. And what it does is that, if you look at all the, value of z, it transforms the, the regular functions into a bounded value output between 0 and 1. So it doesn't matter what the output function is from the theta transpose x, it will, after you put it into the sigmoid function, it will always output values that is bounded between 0 and 1. And this help us solve the problem that we previously encountered with linear regression model. So as I mentioned, logistic regression is an output of probability. So for example, if we feed in the learning model with just two parameters, x0 and x1 being the tumor size, x0 being the intercept, if the learning algorithm h theta x give us a value of 0.7, it means that there's a 70% chance of tumor being malignant. Basically, it is a probability that y equals 0 given the x parameterized by the theta. Yeah, and also for this purpose, the logistic regression model also outputs a value between 0 and 1. And a common way to determine the decision boundary is that we can say that if the decision boundary output is greater than 0.5, then we set the prediction y equals to 1. If the h theta x less than 0.5, y equals 0. It simply means that if the probability is greater than 0.5, then we say, okay, this is a positive prediction. If the probability is less than 0.5, 50%, then we say it is a negative prediction here. Now that I introduced you about logistic regression, we will talk about what is the cost function for the logistic regression and how we can optimize the parameter by minimizing the cost function here. So as you can see, the cost function here for logistic regression is called log loss. It is sometimes referred to as cross entropy as well. And it has two terms. One is that when the y equals to 1, which means that when the target value is 1, the cost function is negative log of h theta x. And if y is 0, which means that if the classification is a negative class, then the cost function between negative log times 1 minus h theta x. And for the cost function, we want to combine both of them, because in our data, we could have positive classes and also negative classes. So to calculate the total cost, we need to combine both of them together. And we combine that by multiply the y for each of the cost function here. The intuition behind it is very simple. Let me explain. So if you look at the first term here, the y times the log of h theta xi, what this means is that, for cases, for classes that is positive, so basically y equals 1, we want to make sure the prediction is as close to 1 as possible. Because as you know, the log of 1 equals to 0. And the log of a very small number is very large. So what that means is that if we're able to predict for all the true or positive classes, if we're able to predict correctly, which means that it's as close to log of 1, then our cost is 0, right? Because we make the correct prediction, therefore our cost becomes 0. But if we make a wrong prediction, basically for true positive classes, if our prediction value is very low, the probability is low, then your costs become high. Vice versa for the second term here, which is 1 minus yi, which is for cases that is 0. If y is 0, then the coefficient here is 1, and the log is 1 minus h theta xi is also the reverse of that. So basically for classes that's negative, we want to make sure that our learning model can have a very low prediction probability as well. If we can do that, then our cost will become close to 0. Otherwise, this cost will become large. So that is the intuition behind this cross entropy formula for the cost function. And to fit the parameters theta, all we want to do is that we want to choose the theta so that this cost function is minimized globally. And here, so that is the cost function. And how do we do that? We will actually use a solution called gradient descent. And what that is that, the methodology is that we start with some, initialized theta, which are the parameters for this cost function. And we will keep changing the theta so that we can reduce the total cost j theta until we end up at a global minimum. A visual representation is a function like here, where the y-axis or z-axis here is the total cost, and you will have the theta 0 and theta 1 as two parameters we want to change, so that the total cost function can move to the global minimum here. So concretely, how do we do that? So here we can utilizing a updates to the j theta by continuously updating this function, the revised cost function here. What the formula here is the theta j will continually equals to the theta j minus the alpha times the derivative of the cost function. What this is that for alpha here is the learning rate. Means that how fast we want to update our theta j parameter. And the derivative of the j theta is the derivative of the cost function. If you remember from your high school calculus, the derivative of a cost function is basically the slope of the function. What that means is that, intuitively, if we are at a point where we initialize the theta j that is very far from the optimal global minimum cost, then at that point, the derivative of this term of this cost function would be large. That means that we want to take a larger step at that point so that we can reach the minimum because the slope is steep. As we get closer and closer to the global minimum, at that point, the derivative here, this term, will become smaller and smaller. And at that point, our update function will take a smaller step so that we can reach the global minimum without going too far away. So the question here, as you can see, the formula is very simple. We start with some initialized theta j, and then we continuously update this function to reach the global minimum with the updated theta j. The key question here is that what is the derivative of the cost function j theta that we derived before? So I'm not going to repeat some of the calculus here. You can find some of the material in your previous courses or previous classes on calculus. But here I'm already have already written out the derivative here, which is a very simple term. So the derivative of the cost function is the h theta xi minus the actual target, the yi, multiplied by the xj. So by using this simple formula, we can repeat this update function to derive at an updated theta j until the convergence. By convergence, what it means here is that the cost function j theta is minimized, and there will be no updates available that can further minimize the j theta. Now that you have learned about the logistic regression, what is a sigmoid function, how do we use gradient descent to update the theta j so that we can minimize the cost of the j theta, I'll talk about the model evaluation after we train the model. For logistic regression model, there are some common ways we can evaluate the model. So there are confusion matrix, precision recall, F1 score, and also the ROC curve. So let's first talk about the confusion matrix here, which is represented by this 2x2 matrix on the right. As you can see, what we do here is in this 2x2 matrix is that we will summarize the data into predicted value, which is prediction from the logistic regression model, and also the actual target, in this format. In this quadrant, you can see that, if the predicted value is positive and the actual is also positive, then we have a true positive. If we have the predicted is positive and the actual is negative, then that is the false positive. Vice versa, if we predicted negative and the actual is also negative, then this is a true negative. And if the predicted is negative and the actual is not positive, then it's a false negative. So the term is pretty self-explanatory by illustrating this with a 2x2 matrix here. For our precision metric, all we do is that we take the true positive divided by the sum of true positive plus false positive. What this means is that the true positive is basically, the predict true and also is actual true. And the TP plus FP is basically all the predicted positive cases. So basically what precision tells us is that out of all the predicted positive cases, what percentage of them is actually correct, right? Similarly, for the concept of recall, it is the numerator is still true positive, but the denominator is true positive plus false negative. So what that means is that out of all the actual positive cases that's out there, what percentage of our model has predicted correctly, right? So that is the concept for recall. And for F1 score, this is basically just a mean between the precision recall, so that sometimes we don't want to work with two metrics, we just want to work with one metric. Then it is common to use F1 score to calculate what is the performance of this model. Other than these precision recall or F1 score, it's also very common to use the ROC curve to understand the performance of the model as well. As I mentioned previously, for precision recall and F1 score, you need to first determine a threshold first on the model in order to calculate them. So for example, we can say if it's the prediction outcome, if it's greater than 0.5, then if it's 1, if it's less than 0.5, it's 0. So we need to determine that first. And the evaluation is based on that decision threshold. However, sometimes we want to understand the rank ordering of the model score, regardless what the threshold we want to choose. And at this point, we will use something like the ROC curve to determine the rank ordering of the model. So the ROC curve, all it does is that the x-axis is the false positive rate, where the y-axis is the true positive rate. So it gives you the holistic view of how the model is performing, against the entire data set of the positive cases. And what we can do, another way to do, to evaluate the metric is that we can calculate the area under the curve here. And this will usually tell us how good the model is as a whole. So this is, we don't need to set a model threshold to determine the quality of this model. Great. So this is all the material for in terms of the high-level theoretical concept for logistic model. Next, let's move to a actual concrete example to illustrate how we can build a logistic regression model. So now let's look at an actual example of implementing logistic regression with Python. And in this example, we'll use a pretty famous data set called Titanic data set from the Kaggle competition. So we'll predict the classification model, binary classification of whether someone is survived or deceased through this data. So let's start. So let's start by implementing some of the key libraries from the Python, pandas, numpy, and pyplot. We'll also import the seaborn shell so that we can have a nicer graph from the plot. We will, first import the data through the read.csv. So I have already downloaded the Titanic CSV files on my local drive. So have imported that. First thing we can take a look is just take a look at the first 5 rows from this data using the .head function. So here you can see that, it's just a very simple data set. Here, the survive is the target or the Y that we will try to predict. So the 1 means that they have survived and 0 means that they have not survived. So we have names. The class basically is what class of the cabin that these customers reside. The name of the customers, the sex, age, how many siblings they have, how many parts they have, the ticket number, the fare value, the actual cabin, and also embarked, boat, body, and home destinations. Obviously, there are a lot of features here that is very useful in determining whether the customer has survived, but we also potentially have some features that's completely unrelated to this as well. So let's first take a look at the null value for this data. So we want to explore whether the data is in good shape. So we can use the heat map here from the seaborn to check what is the null distribution here. So we can see that couple of features have a lot of nulls. For example, the age, the cabin, the boat, body, home destination. These all have nulls, whereas the cabin, boat, body have majority of these features are nulls. We can also take a look at how many records are there in this data set. Alternatively, you can also check the information of the data set with the .info. This is a useful function where you can see all the features we have and how many of them are non-null as well, and also the data type for each of the feature. Yeah, so the next we want to do some exploration on the bivariate analysis, which is looking at the target, which is a survive, yes or no, by different features. So here we can look at, whether someone survived, as a whole in this data set. And we can also separate this by gender. So we can look at, what is the survival count by each of the gender. So here you can see that, with survive 1, you can see that, there are actually more females survive than the male versus, the non-survive cohort. So which means that, they probably let the women to board the boat to escape before the men for majority of the cases. Here we also can look at, the survival rate or the survival counts by the class. So here, as you can imagine, the first class customers have a lot more, survivors than other classes, even though the first class have the lowest total amount of people. The other useful technique we can look at is look at the histogram of the customer age. So here we can easily plot the histogram with the building function to look at the distribution. You can see that, it is kind of a bimodal distribution where you have certain cases that, we have nulls, which is grouped here in the left, far left corner here. And the rest are, I would say the peak is around 20, between 20 to 25, the age of 20 to 25. So, that accounts for majority of the people on Titanic. Next one, we can count, look at how many people have siblings for all the customers. And we can see that, majority of the customer, they don't have any siblings. And then the next one would, be, 1 siblings and then 2 siblings. Most, maximum case, you have, 6 siblings on the chart, but only very few customers have 6 siblings boarding the ship. The next one, we can also take a look at the fair price. So here you can see it is a very right skew distribution where, it goes all the way to $600 to the right here. So next, we can also take a look at the, the dot plots charts by looking at, different classes by age. So here you can see that, the first class customers, they're, compared to other classes, they're more likely to be older, which makes sense because, likely these older folks have, are wealthier, so they can afford the first class, versus probably a lot younger people that are staying in the first class as well. So as I mentioned, age is a feature that has a lot of missing. So here we can build a function to input the age by looking at the average of the P classes. As you can see from the previous chart, that where you live on the board in terms of a class has a high correlation with the age. So for all the missing ages that we have, if we look at the class that they're in, we can use the mean to impute it. So this is what this module does, and then we can use the dot apply, which is a built-in Python function, to input the missing ages by using the class. And after that, we can check the dot is null. We can see a majority of these ages don't have nulls anymore, and the only nulls we have is the fair. And then we can drop all these columns that is not necessary or is unrelated to the survival rate. And that will do the, and also drop the NA for the rest of the cases. So that completes the null imputation part of the exercise. The next one is to create these, converting these categorical features. So as we can see, we have sex and embark features. That is, in categorical feature, we can use the get dummy function from pandas to create a dummy features, which is one hot encoding. The drop first equal true here means that we don't want to create all the features for the categorical features because we only need n-1 columns for these one hot encodings. Again, after we create these, we can further drop these categorical features. And we want to concatenate the original data set with the newly created dummy features as well. And yeah, that's all for the data preparation for the model. For the next one, we can use the sklearn to import the train test splits. In order to build this model, we want to separate the model into training and testing set. So we can easily use the train test split, and split this data. So here we use the test sample of points rate, which means that we will keep 30% of the cases as a testing sample set. So here, the next step is to actually train the model. So here we use the logistic regression to train the model. So X is the feature and Y is the target for the training set. And for the prediction, we want to predict using the train model to predict the features from the test set. So at this point, we have finished just with straight lines of code. We have finished training the model. The last stage is just to look at the evaluation. So here we can import the classification report from sklearn, and by looking at the the target versus the prediction that we created using logistic regression, we can look at what is the precision, recall, F1 score for different cases. So here, we have precision and recall for both classes. So 0 means that the non-survived class, and then 10 is the survived class. So here you can see that for the survived cases, the model has a 74% precision and 74% recall. Yeah, so that's all for today's lesson. So hopefully you can learn something from today's lesson, and thank you, everyone.